HTTP streaming. How HTTP streaming can improve page performance and how Airbnb enabled it on existing codebases. This is a post by Victor from the Airbnb tech blog. Okay, so this should be interesting because it's from the actual Airbnb tech blog. So I wonder why Airbnb needs streaming. Let's see, maybe in order to update things on the screen. I take it it's not for video, but for updating stuff on the screen continuously. Let's see. Introduction. You may have heard a joke that the internet is a series of tubes. In this blog post, I'm not aware of this joke. In this blog post, we are going to talk about how we get a cool, refreshing stream of Airbnb.com bytes. Yes, so it's streaming of the bytes does not necessarily mean video into your browser as quickly as possible using HTTP streaming. Let's first understand what streaming means. Imagine we had a spigot and two options. What is a spigot? Okay. Spigot, maybe it's some kind of coffee. Fill a big cup, yes. Fill a big cup and then pour it all down the tube, the buffered strategy. Concat the spigot directly to the tube, the streaming strategy. Okay. So I have second thoughts about streaming because I feel like if I need to process some data, then in most cases, streaming would be the optimization that would come with these advantages. Meaning I would always prefer to see the whole data. Somehow it's both easier to manipulate, and I take it both for the data offline world and also for the online world. I prefer to see the whole picture and work on it unless the optimization is something that has a real effect and not just playing with numbers. Let's not be negative and see how it helped them. In the buffered strategy, everything happens sequentially. Yeah, our servers first generate the entire response into a buffer, filling the cup. Okay, so first we fill the cup, I like it, and then more time is spent sending it over the network, pouring it down. Okay, so they fill a buffer that they have, right? They have like this is the server, so the server is filling a buffer, and then they are sending it, once the buffer is full, sending it to the client, which are sent as soon as they are ready. The server can start working on the next chunk while previous chunks are still being sent. Yep. And the client, example, a browser, can begin handling the response before it has been fully received. Implementing streaming at Airbnb. So streaming is the other way where you continuously send your data from the servers to the client. Specifically here, they talk about sending data from the server to the client, whether it should be first fill the buffer, send to the client, or just send continuously the bytes. Streaming has been clear advantages, but most websites today still rely on buffered approach to generate responses. Interesting. One reason for this is the additional engineering effort, required to break the page into independent chunks. This just isn't feasible sometimes. It would require effort, and just think of the troubleshooting and debugging, whether it's going to be worth it. For example, if all the content on the page relies on a slow backend query, then we won't be able to send anything until the query finishes. However, there's one use case that's universally applicable. We can use streaming to reduce network waterfalls. This term refers to when one network request triggers another, resulting in a cascade series of sequential requests. So when we have this cascading sequential request, then one would wait for the other, would wait for the other, would wait for the other, which is not good. Because this can then be really cause high latency. This is easily visualized in tools like Chrome's waterfall. So we see here the cascading here. Each request, some of the requests at least, wait for the previous one to complete. So we really get high latency. Most web pages rely on external JavaScript and CSS files linked within the HTML, resulting in a network waterfall. Downloaded the HTML triggers, JavaScript, and CSS downloads. As a result, it's a best practice to place all CSS and JavaScript tags near the beginning of the HTML on the head tag. This ensures that the browser sees them earlier. So we are trying to compete and put all the CSS and JavaScript earlier. With streaming, we can reduce this delay further by sending that portion of the head tag first. What's the difference? We said that here we put it on the beginning of the HTML head tag, and now we said that I guess the thing here is that somehow they send the portion of the head tag first. Let's see more details, and now didn't fully follow them. Early flash, the most straightforward way to send an early. Okay, so now they explain how they send early the head tag. Early flash. The most straightforward way to send an early head tag is by breaking a standard response into two parts. This technique is called early flash, as one part is sent flashed before the other. The first part contains things that are fast to compute and can be sent quickly. At Airbnb, we include tags for the font, CSS, and JavaScript, so that we get interesting. So if you need some JavaScript to appear to already get to the client, you put them early and send them early and flash them early. What does exactly flash early means? They would probably here utilize the streaming, so that we get the browser benefits mentioned above. The second part containing the rest of the page, including the content that relies on APIs or database queries to compute, the end results look like this. So here is the early chunk. We see HTML, head, JavaScript, SRC, link rel. Okay, so we have here the JavaScript and CSS, and the late chunk is the actual HTML. We had to restructure our app to make this possible. For example, for context, Airbnb uses Express-based Node.js servers, interesting to know, to render web pages using React. We previously had a single React component in charge of rendering the complete HTML document. However, this presented two problems. So React components, you have some main component and some child components. So they said that they first had a single component, but they had issues with this optimization with this. Producing incremental chunks of content means we need to work with partial unclosed HTML tags. Okay, this is where the complexity comes. Still question whether it's worth it. For example, the examples you saw above are invalid HTML. The HTML Why? Why invalid? The HTML and head tags are opened in the early chunk, but closed on the late chunk. Okay, so it's split, yeah. Yeah, so it's a problem. So the browser would get like partially of the HTML and only some of it. There's no way to generate this sort of output using the standard React rendering function. So what would the browser do if I get HT instead of HTML? We can't render this component until we have all the data for it. We solve this problem by breaking our monolith component into three: an early head component, a late head component for head tags that depends on data, and the body component. So this is super interesting because we see here an actual deep optimization of an HTML page, which goes beyond reducing the size. I wonder if there are alternatives, simpler alternatives to this. Each component renders because I really don't like doing this optimization unless it's really something that we need. And unless there is no other optimization simpler that we could do. Maybe we could make the server faster or something, so we would not need to deal with all this complexity, but I take it that if they reach the conclusion they need it, then I guess they needed it. Each component renders the content of the head or body tag. When we stitch them together by writing open-close tags directly to the HTTP response stream, overall the process looked like this. Write HTML head, yeah. 2. Render and write the early head to the response. 3. Wait for the data. 4. Render and write the late head to the response. 5. Write /head and begin body. 6. Render and write the body to the response. 7. Finish up by writing the closing body and closing HTML. Data streaming. Early Flash optimizes CSS and JavaScript network waterfalls. However, users will still be staring at a blank page until the body tag arrives. We'd like to improve this by rendering a loading state when there is no data, which gets replaced once the data arrives. How this loading page helps someone? I would see a loading page. Okay, so they want to avoid this blank page. Conveniently, we already have loading states in this situation for client-side routing, so we could accomplish this by just rendering the app without waiting for the data. Unfortunately, this caused another network waterfall. Browsers have to receive the SSR server-side render, and then JavaScript triggers another network to fetch the actual data. So the loading is probably the SSR, the server-side rendering, and now we get the client-side data. In our testing, this resulted in a slower total loading time. So now we have even slower loading time. What if we could include this data in the HTML? So already generate the HTML with this, but we said that the body was not sent yet. This would allow our server-side rendering and data fetching to happen in parallel. What if we could include this data in the HTML? Okay. Given that we had already broken the page into 2 chunks, with early Flash, it's relatively straightforward to introduce a third chunk for what we call deferred data. This chunk goes after all the visible content. So we are trying to send the loading with the HTML page. We're trying now to split the page into 3 sections. The visible content, it does not block rendering. We execute the network requests on the server and stream the responses into the deferred data chunk. In the end, our chunk looks like this. Okay, so we have the early chunk. Each start, begin HTML, begin head, CSS, JavaScript, body chunk, which includes the opening body, deferred data chunk, which includes the closing body and all the data of the HTML data. With this implemented on the server, the only remaining task is to write some JavaScript to detect when our deferred data chunk arrives. I think at least the good part on this is that it can become generic and become the basic infrastructure for all pages. We did this with Mutation Observer, which is an efficient way to observe DOM changes. Just think about debugging this. How much did it save you? Actually, let's see later. Once the deferred data JSON element is detected, we parse the result and injected it into our application network's data store. From the application perspective, it's as though a normal network request has been completed. Watch out for defer. You may notice that some tags are reordered from early Flash. Example, these script tags moved from early chunk to the body chunk and no longer have the defer attribute. This attribute avoids render blocking script execution by deferring the script until after the HTML has been downloaded and parsed. This is suboptimal when using deferred data, as all of the visible content has already been received by the end of the body chunk, and we no longer worry about render blocking at that point. We can fix this by improving the script tags to the end of the body chunk and removing the defer attribute moving. It's beginning to get funny. The tags later in the document does introduce a network waterfall, which we solve by adding a preload tags into the early chunk. Good. Implementation challenges, status codes and headers. Early flash prevents subsequent changes to the headers. Buffering. We found that Nginx buffer responses by default and they needed the streaming. They said this has resource utilization benefits but is counterproductive when the call is sending incremental responses. We had to configure these services to disable buffering. Oh my god. And we expected the potential increase in resource usage with this, but found the impact to be negligible. Responses delay, we noticed that with the early flash responses had an unexpected delays of 200 milliseconds, which disappeared when we disabled gzip compression. This turned out to be an interaction between Nagel's algorithm delayed ACK. So there are all these playings when Nagel's algorithm, I think it just means that if it got a little snippet from the server, it would wait for more. These optimizations attempt to maximize the data sent per packet. So they wait for sending the packets. They say, okay, I have only 100 bytes. Let's not send them yet. Introducing latency when sending, and you can disable this. When sending small amounts of data, it's especially easy to run into these issues with jumbo frames. Jumbo frames, I think it's for networking when you want the frame to have higher size and to optimize, which increases maximum packet sizes. Turns out that gzip reduces the size of our writes. So when they use gzip, the size of the writes, they were smaller. So then Nagel's algorithms took action and blocked the sending of the packets. And the solution was to disable. This is usually what happens. You eventually need to disable Nagel's algorithm in our HA proxy load balancer. Conclusion. Wait, but how much time did you save? Let's hope they mention it in the conclusion. Was it worth the effort? Because this looks big, huge effort, I think. Conclusion. HTTP streaming has been very successful strategy for improving web performance at Airbnb. Our experiments show that early flash produced a flat reduction in first contentful paint of around 100 milliseconds. Okay, so if you multiply 100 milliseconds by all the users, then this is good. If it's actually the case, because if it's actually for all the pages, who knows? Maybe there are some pages where it didn't affect, but on these cases, the best thing to do would be to ground this performance optimization in some test, and if someone makes things slower, then the continuous deployment should fail the build. Including because today we can save this 100 milliseconds, tomorrow it will increase. So what did we do exactly? Okay. Including the Airbnb homepage, data streaming further eliminated the FCP, first content cost of slow backend queries. While there were challenges along the way, we found that adapting our existing React application to support streaming was very feasible, robust, despite not being designed for it originally. We're also excited to see. I would hope to see much more statistics and data than just saying, after all this effort, we reduced 100 milliseconds. I would expect much more statistics. Whether you're using these new technologies or, but it's still interesting to know the streaming and the split of requests. And of course, now, thanks to everybody, let's give them some claps.